This is Chandrayaan-3, one of India's most ambitious space programs. In this video, we will explore in detail the lander, the rover, and all of their scientific payloads. On July 14, 2023, India launched Chandrayaan-3, atop one of its most powerful rockets, the LVM-3-M4. The spacecraft commenced its journey towards the Moon. Following 5 orbit-raising maneuvers, the spacecraft was inserted into a translunar orbit. After additional deorbit burns, on August 20, 2023, nearly 40 days after its launch, the spacecraft detached from the propulsion module, preparing for its lunar landing. The first significant milestone in this mission is the rough braking phase. The main 4 engines on the spacecraft are ignited for a duration of 690 seconds, when the spacecraft is closest to the Moon's surface, approximately 30 kilometers above it. These engines are capable of producing thrusts of 800 newtons each and are throttleable, allowing thrust adjustments between 40% to 100%. They run on a fuel mixture of monomethyl hydrazine and nitrogen tetroxide. During this rough braking phase, these engines reduce the spacecraft's horizontal speed from 1.68 kilometers per second to 358 meters per second. As a result, the spacecraft gets remarkably close to the Moon's surface, reducing its altitude from 30 kilometers to just 7.4 kilometers. As the spacecraft descends towards the Moon's surface, it operates autonomously, relying on a variety of sensors and cameras for status monitoring, error correction, and navigation. Towards the back of the lander, you'll find the LHVC, or Lander Horizontal Velocity Camera. This camera continuously captures images of the lunar surface, and calculates the horizontal velocity of the lander, by analyzing the differences between consecutive pictures. Just below the LHVC is the LPDC, or Lander Position Detection Camera. It also continuously captures images, to determine the precise location of the spacecraft. During its mission, the previous spacecraft, Chandrayaan-2, provided highly detailed images of the landing site, and these images are pre-stored in the Vikram lander. This camera compares the images of the lunar surface with the pre-stored images of the landing site, allowing for an accurate assessment of the spacecraft's location relative to the intended landing site. During its journey from Earth to the Moon, these 2 cameras, also called as the star sensors, help the spacecraft track its location, based on star maps. The star sensors can compare the observed star patterns, with known star maps, to determine the spacecraft's position in space. Following the 690 seconds of rough braking phase, the mission transitions into the fine braking phase, maneuvered with more precise control. During this phase, only 2 out of the 4 engines are actively producing thrust, while the other 2 engines are turned off. Over the course of approximately 175 seconds, these 2 primary engines, along with 8 small thrusters, work together to reduce the horizontal velocity of the lander from 358 meters per second to 0, and orient the spacecraft vertically. These 8 small thrusters, also called as attitude thrusters, each generating 58 newtons of thrust, operate on hypergolic fuel. They play a crucial role in controlling the direction of the lander, by delivering small, pulsed thrusts. These thrusters allow for precise steering and directional changes. 4 reaction wheels are also mounted on the top of the lander, for further adjustments to the lander's direction and angle. These stepper motors spin as needed, and the heavy wheels attached to them also spin. Following Newton's third law of motion, it produces a reaction that rotates the lander in the opposite direction. By controlling the combination of rotations of these four reaction wheels, the lander is controlled precisely during the descent phase. As this fine braking phase comes to an end, the lander is allowed to hover stationary, 700 meters above the lunar surface. During this 12 seconds of hovering, the landing site is thoroughly checked, verified, and it is made sure that there are no big craters below the lander. This analysis is done by the LHDAC, or Lander Hazard Detection and Avoidance Camera at the front of the spacecraft. This camera is very important as it helps to avoid any large craters on the landing site. If this camera detects any large craters, the lander moves maximum of 150 meters away from this area and searches for a new landing site which is relatively smooth and flat. In the final phase of the descent, for the next 22 seconds, the lander descends gradually, from an altitude of 800 meters, down to 0 meters. At the end of this critical period, all engines are switched off, allowing the lander to make a soft landing on the lunar surface. To absorb the shock of landing, all four legs of the lander are equipped with crush cores. These crush cores are constructed using a honeycomb structure, made of aluminum. Upon impact with the lunar surface, these crush cores compress and deform, effectively absorbing and dissipating the landing shocks, ensuring a gentle and controlled landing. During the critical landing maneuver, the lander continuously sends data to Earth, allowing us to monitor its health and critical parameters. This communication is facilitated through several antennas on the lander, each serving a specific purpose. There are two main types of antennas on board. One is the TTC antenna, which stands for telemetry, tracking, and command. These TTC antennas handle all communication signals to and from the Chandrayaan lander, and are highly reliable, capable of long-distance communication. There are three pairs of TTC antennas on the lander. One at the front, one at the back, and one on top. These cylindrical structures have quadrifilar helix antennas in them, with four filaments wound in a spring-like helix on a core. Each TTC structure contains two cylindrical antennas, one for receiving data and one for transmitting. The presence of two pairs ensures redundancy, so that regardless of the lander's orientation, at least one of the pairs is directly in contact and capable of sending and receiving data to and from Earth without interruptions. On Earth, this data is received by the Indian Deep Space Network, or IDFN. One pair of antennas on the top of the lander is used to communicate with Chandrayaan-2's orbiter and serves as a backup link. The second type of antenna on the lander is the X-band antenna. This antenna is movable, with two motors to adjust its direction as needed. It offers high-speed data transmission. The X-band antenna is primarily used to transmit images, captured by various cameras on board the lander and the rover, as well as data, collected by the scientific instruments. The lander and the rover are like a laboratory on the surface of the moon, where it will conduct all sorts of experiments and gather a wealth of data. Let's dive deep into all of the scientific instruments on board. We'll explore what they do, why they're important, and how they're helping us uncover the moon's mysteries. The first scientific instrument on board the lander is Chandra's Surface Thermo-Physical Experiment, or CHASTY for short. In simple language, this experiment is like a tool to help scientists understand how hot or cold the moon's surface is. The experiment has two main goals: to measure vertical temperature gradient and the thermal conductivity of Moon's soil. When the spacecraft lands on the Moon, the temperature probe is deployed. A motor moves the tool and makes it stand up straight on the Moon's ground. Another motor helps the tool go into the Moon's soil about 10 centimeters deep. The tool has 10 temperature sensors on its surface. These sensors are called platinum RTDs. RTD stands for Resistance Temperature Detector. They're made of super thin wires of platinum metal. The sensors change their electrical resistance when the temperature changes. Then a suitable electronic circuit is used to measure this change in resistance. These platinum sensors can tell us the temperature from -200 to 800 degrees Celsius, and with the accuracy of about 0.1 degrees Celsius. These sensors help us find the vertical temperature gradient of the Moon's surface. The temperature probe also has a heater around the sensors. This heater is made of a flexible material called polyamide. When electric current is sent through the heater, it warms up the soil around the sensors. By observing the changing values of the temperature sensors, we can know how the heat moves, and we can learn how good the soil is at carrying heat. This helps us know the value of the thermal conductivity of the lunar soil. The second scientific instrument on board is the Instrument for Lunar Seismic Activity Studies, or ILSA for short. Its primary purpose is to measure the movement of the Moon's surface, just like the earthquakes on Earth. ILSA is located at the front of the lander, encased for protection. When the rover's ramp opens and extends to the lunar surface, this instrument is brought closer to the lunar soil. To deploy it, a frangibolt is utilized. This is an actuator operates on the principle of shape memory alloy. When heated, it expands and cuts the bolts holding the instrument. As a result, the instrument is deployed on the lunar surface. Within the ILSA package, there are two sensors based on MEMS technology, which stands for Micro-Electro-Mechanical System. Essentially, these sensors consist of a comb-like structure made of silicon. The central part is movable and connected by thin supports, while the other part remains stationary. If any activity occurs on the Moon's surface, such as a moonquake, the instrument experiences shaking. The movable portion of the electrode acts as a spring. It moves and alters the gap between the electrodes. This change in gap changes a capacitance value, which is recorded through suitable electronic circuitry. ILSA has two such sensors inside. One is a coarse sensor and the other is a fine sensor. It allows data collection at varying levels of accuracy. This data is subsequently analyzed to study the seismic activity or movement of the Moon's surface. RUMBA, which stands for Radio Anatomy of Moonbound Hypersensitive Atmosphere and Ionosphere, is an instrument designed to study the electron density of the Moon's atmosphere. Yes, you heard that correctly, the Moon has a very thin atmosphere. It's not a perfect vacuum. Previous experiments have revealed the presence of plasma in the Moon's tenuous atmosphere. Plasma consists of tiny charged particles. The density of these tiny charged particles varies across different regions. The tool is used to measure how densely these charged particles are distributed in the Moon's thin atmosphere and how this density changes over time. The instrument consists of a spherical probe made from a titanium alloy attached to a non-conductive rod. Together, they form a Langmuir probe, an instrument used in various applications to measure free electron densities. The probe is connected to the lander at one end using a spring, and it is held close to the lander, with a hold and release mechanism. Upon command, this mechanism releases the probe, allowing it to be deployed into the Moon's thin atmosphere. The metal sphere at the end of the probe carries a positive charge, attracting free electrons in the atmosphere. This attraction generates tiny electric currents in the probe, which are then measured to calculate the electron density in the lunar atmosphere. Few hours after lander has settled on the Moon's surface, the rover named Pragyan comes out from the belly of the lander and deploys its solar panel. The rover will be busy for next 14 days, wandering on the lunar surface and collecting valuable data. The rover is small, about the size of a suitcase, and weighs 27 kilograms. It is packed with instruments for navigation, observation and research. Let's look at the scientific instruments on board the rover. The Pragyan rover carries with it the APXS, Alpha Particle X-ray Spectrometer. This device is designed to analyze the composition of materials, such as rocks and minerals, that make the lunar landscape. But how does it work? Every matter consists of atoms, and atoms comprise a nucleus, with electrons orbiting around it. These electrons do not revolve randomly in just any orbit. Instead, they exist in specific energy levels. The smaller the orbit, the lower the energy. Therefore, electrons in the innermost orbits have lower energies, compared to those in the outer orbits. These electrons can transition from one energy level to another. The instrument comprises two parts, an emitter and a detector. Do you see these 6 capsules? These capsules contain a radioactive element called curium, which emits X-rays and alpha radiations by itself, due to its property of radioactivity. These radiations carry energy, and when directed at any material, they can knock off some electrons from the atoms in the low-energy inner orbits. When these inner electrons are displaced, the atom becomes unstable. To regain stability, outer electrons may transition into these lower energy levels, releasing energy in the form of X-rays, with unique energies characteristic of different elements. It's like a unique fingerprints on different people. A detector, known as an SDD or silicon drift detector, is there at the center of the emission ring, to capture these characteristic X-rays emitted by each element. The silicon drift detector, made from semiconductor material silicon, effectively detects X-rays, since interactions between X-rays and silicon generate electric signals. The alteration in the electric signal is directly proportional to the energy of the incoming X-rays. With the help of suitable electronic circuitry, these signals can be processed, and the elements are detected. When not in use, to save instrument from lunar dust and debris, sensitive parts of the instrument are covered by a cover plate. This cover plate is also a calibration target plate. The plate has 4 elements attached to it: stainless steel, copper, titanium, and aluminium. It is used to calibrate the instrument before use, to make sure the readings taken by the instrument are accurate. The instrument is open to the lunar dust and debris when the readings are taken, and it can be retracted to increase the rover's ground clearance while moving. Another instrument on board is the laser-induced breakdown spectroscope, abbreviated as LIBS. It employs a different technique to analyze the elemental composition of lunar soil and rocks. The LIBS instrument consists of several components: a pulsed laser source, a collector, optical lenses and mirrors. It functions by directing a powerful laser beam onto the lunar rock or soil sample in high-energy, short pulses. This process generates a very small region, with extremely high temperatures, causing the material to vaporize, and become plasma with excited atoms. Excited atoms are the atoms in which electrons absorb the laser energy and transition to higher energy orbits. Subsequently, when a relaxation period is given, these electrons return to their original energy levels, emitting characteristic electromagnetic radiation. Lenses collect this emitted electromagnetic radiation. This is then passed to the spectroscope with a set of mirrors inside the instrument. The spectrometer separates the different wavelengths of the collected radiation. This separated electromagnetic spectrum is distinctive for different materials, enabling the identification of different elemental compositions. During navigation, the rover utilizes two 1-megapixel black and white cameras, known as NAV cams. These cameras offer a 3D view of the rover's surroundings, and they help in creation of digital elevation maps and the planning of future routes. For the rover's movement, a rocker bogie system is designed, equipped with 6 wheels. Each wheel is driven by an independent brushless DC motor. To power all the payloads and other instruments, the rover requires approximately 50 watts of power. This power is supplied by the solar panel on the rover. When the solar panel is not deployed, the rover needs an additional power source to move out of the lander and deploy the solar panel. This initial power is provided by lithium-ion batteries, located inside the rover's body. Within the rover's body, various other components can be found, including the REC card, which stores all the data collected by the payloads and cameras. Additionally, there is an RxTX package that helps in receiving and transmitting data with the lander, using the antenna positioned on top of the solar panel. A differential gear arrangement inside the body, connecting 2 axles of the wheels, ensures the movement is distributed in a manner that keeps the rover's main body approximately straight and parallel to the ground during motion. The wheels of the rover have an Indian national emblem and logo of the Indian Space Research Organization. As the rover moves on the moon's surface, it leaves its mark on the moon's surface. These symbols, etched into the lunar dust, will stand as a testament to the dedication, passion, and perseverance of the countless scientists, engineers, and visionaries who made this journey possible. Chandrayaan-3's journey may have reached its destination, but the story of exploration, of pushing boundaries, and reaching for the stars, that story continues. It's a story written in the stars, and it's a story that belongs to us all.